This video is on population dynamics and community relationships. Let's start with the hierarchy of organization. First, we have our organism. I'm going to give you examples of each of these. Like, let's say we have a starfish. And then a population is a group of the same organisms. So we can have a galaxy of starfish. And then a community is a bunch of groups of populations. So these are all the biotic or living things in your environment, okay? So this includes multiple populations. For example, you could have your starfish. You could have your shark. You could have your corals. All of these are living. You could have your algae and other types of things that do photosynthesis. You could have bacteria. These are all part of the community because they're all living. In a forest ecosystem, trees are part of the community because they're living. An ecosystem is a combination of the biotic, the community organisms, and the abiotic, the non-living things. So an ecosystem includes the community plus abiotic factors, for example, in this example, like water, sand, sun, currents, like wind currents and sea currents, things like this. And then a biome is a group of related ecosystems. For example, like the ocean or the Great Barrier Reef would be a biome. So today we're going to focus primarily on populations and communities, and we're going to start with population growth models. Population growth models look scary at first because if you see this, you think to yourself, oh my gosh, I'm looking at a derivative. But you do not have to think of this as a derivative. We're going to think of this as a single variable, like this could be the variable x, okay? This variable, even though we know it's a derivative, stands for population growth. Population growth equals the number of births in the population minus the number of deaths in the population. In an exponential growth model, you have uncontrolled growth like this. So over time, there's just rapid growth in this population. And the equation used to calculate exponential growth would again be dn over dt, which is population growth, equals R max, and R max stands for the growth rate. And your growth rate is usually like from 0.1 to 1. And your growth rate is really birth rate minus death rate. And then the N stands for number of individuals in a population. So if you wanted to calculate exponential growth, you would use this equation. And this would give you the increase in the number of individuals in the population over a certain period of time. But when would a population be in exponential growth? We're looking at times when nothing is stopping their growth or holding it back. So you would have to have unlimited resources, right? No predators or disease or competition. And really good examples of things that are in exponential growth right now are invasive species. Like when the fish head came over, the snake head came over, right? And I see tons of snake heads at Huntley Meadows all the time. They don't have any predators. They can eat anything. There's tons of space, and they're not competing for resources, right? So they just grow and grow and grow. And there's not a lot of diseases that affect them here. Humans, unfortunately, are still kind of in exponential growth, but as we cause all these impacts on the earth, that stops as well. Okay, so that's not the only way populations can grow. And in fact, that's not the primary way populations grow. When we think about how populations grow, we're often looking at logistic growth. Logistic growth is the idea that when the environment when environmental pressures impact organisms, this slows growth rate. So an exponential growth curve may look like a logistic growth curve may look like exponential growth at first, and then it kind of levels off, and then it plateaus and oscillates around K, which stands for carrying capacity. So a logistic growth model shows exponential growth at first, and then a slowdown because of environmental pressures, and then a plateau, and then they oscillate around the K, which stands for carrying capacity. So when you look over here at the equation for logistic growth, you have to take into account the carrying capacity. And as you get close to carrying capacity, growth slows a lot. Again, we start with population growth over here. We have R max, which is the growth rate, times the total number of individuals in the population, or N. And then this is when we take into account carrying capacity. We have carrying capacity minus the total number of individuals over carrying capacity times all of this. And again, that takes into account this variable right here. So carrying capacity is the total number of organisms in a population that the environment can support. And there are things that affect carrying capacity, and we're going to look at kind of two things that affect carrying capacity right here. These are things that can impact carrying capacity. Okay, these are the environmental pressures we've been talking about. The first are density-dependent factors. These are factors that are impacted by density. So if we think about a population, okay, what would slow their growth and slow their growth more the more dense the population was? So we're looking at things like diseases. When populations are more dense, diseases spread more rapidly. Or like lack of resources or competition. When there are more people when there are more organisms at the watering hole, there's less water for all the organisms. And same thing with predation. When there are a lot of prey, they get packed together, it attracts predators, they can't hide, they might be predated on. Density-independent factors, however, are not affected by population density. However, they do still limit population growth. These are things like natural disasters, climate change, although sometimes that can be density dependent as well, and human impact. So if we move from populations to communities, so populations, okay, let's look at their growth rate, and then communities are how populations interact. So when you look at community interactions, you're often going to see graphs like this. And in this graph, you can see, okay, here's the years down here, here are the moose and the wolves. So this is a classic predator and prey graph. And in this predator and prey graph, you can kind of see, right, like here is the wolf population and here's the moose population. And you can see as the moose population grows, if I can get this, as the moose population grows, right, then there's more food for the wolves to eat, so the wolf population grows, right? And then there's too many wolves, they kill off too many moose, and so their population declines as well, right? So you see this bump up in moose first. So this moose population bumps up, and then that causes the wolves to have more food, so the wolf population starts to bump up. And then, too many wolves, the moose die off. There's no food for the wolves die off. Then, there's not as many predators, so now there's more moose, right? And so then that will cause the wolf population to grow and so on. All right, I might have done them backwards, but you get the point there, okay? So you need to really, in communities, you really need to look at interactions between populations, okay? And there's two main things to look at. The first one that we need to look at is energy and matter. So remember, energy flows. We can start with solar energy or chemical energy, and it's going to flow from one organism to another. Matter, however, right? Matter cycles, nutrient cycle. So if we think about like the water cycle or the nitrogen cycle or things like that. And one of the main things you need to worry about on the AP exam is how change affects these processes, right? So like how would a change in light, temperature, water impact organisms and their access to matter and energy, right? So for example, if we think about animals, they get their nutrients and energy from their food, right? If we think about plants, right, they get their energy from the sun and they get their nutrients from the soil. So you can think about like, oh, lack of light, how would that affect the rate of photosynthesis and things like that. We can also think about relationships between organisms within a community, right? And this can be modeled pretty effectively. So the plus is going to stand for positive, and the minus is going to stand for negative. So for instance, with competition, that would have a negative effect on both organisms because one might win, but they probably are both injured or lose out on something. And predation, it's a positive effect for one, they get food, and the other one is dead. Just sad. And then symbioses are these close permanent relationships. Mutualism is when both organisms benefit, like a pollinator and a flower. Parasitism is when one organism benefits and one is harmed, like a tick on a dog. Commensalism is when one benefits and one does not care. It's kind of neutral. So those are community interactions. So if I've just asked you to watch the Big Sheet video, you can stop here. If you're also doing population practice problems, continue on and watch the population growth practice problem piece. And that means you, AP Bio. We're going to do the population growth practice problems. So let's focus on these population growth practice problems. Okay? You're going to do problems 1 through 9, and I'm going to do number 2 and number 4 with you. So you'll have to think about the two equations that you got and determine whether each practice problem is asking about an exponential growth rate or a logistic growth rate. Let's do 2. There are 780 turkeys living in Marion Township. The birth rate is 0.472 turkeys per year, and the death rate is 0.331 turkeys per year. We know that R max equals birth rate minus death rate. So that's the first thing that we need to calculate, right? R max is 0.472 minus 0.331, right? So R max is 0.141. Okay. The next thing you need to do is think about, is this problem asking you for exponential or logistic growth? Predict the number of turkeys after 1 year, assuming that the growth rate stays constant, so that's R max, and the turkeys are not close to their carrying capacity. So if they're not close to their carrying capacity, okay, then they're in exponential growth. So we're going to use the equation dn over dt equals R max times the number of organisms in the population. So in this case, we calculated R max. R max is 0.141. And the total number of organisms in the population at the beginning are 780 turkeys. Okay, so 0.141 times 780. I'll give you a second to calculate that. So I got 109.98. Well, you can't have 0.98 of a turkey, I guess, unless you cut off its toes. So we'll round up to 110 turkeys. This is the new turkeys in the population. So to get the total number of turkeys in the population after 1 year, you're going to take 780 turkeys, the initial population size, and add 110. So after 1 year, there are going to be 890 turkeys in Marion Township. Now, oftentimes students are confused because they say, Miss Kinney, how can you add 110 to 780? Like, what if some of these original turkeys died? This 110 number does not mean 110 turkeys were born. This means the population increased by 110. Because remember, our max takes into account birth rate and death rate. So this 110 says, oh, from the 780 turkeys, we increased in population by 110. So there are 890 total turkeys. Okay. So let's say like 10 turkeys died and 120 turkeys were born. Well, this number is like the additional number added to the population. So I also would like you to do question number 1 and question number 3 as well. Those are on exponential growth. Like quick tip, the original population here starts as 40. Whatever the final population is after 1 month, that's the starting population for month 2. The final population at the end of month 2 is the starting population for month 3. Let's do 4 as an example as well to round things out, because 4 is a different type of problem. So let's look at 4. There are 45 geese in a population in a general ecosystem. If R equals 0.72 geese per year, so they already gave you R max, you didn't have to calculate it, which is kind of nice. And the carrying capacity is 50. So if they say carrying capacity, we know we're looking at the logistic growth model. What will the population of the flock be 1 year later? So again, we can write our equation. The amount of population growth equals R max, the population size, the population growth rate times N, the population size, and then we're taking into account the carrying capacity, right? So R max is 0.72 times the population size, 45, times the carrying capacity, minus the number of organisms of the population over the carrying capacity. So I'll give you a second to calculate that. Okay, so I got 3.24. So the population size is going to increase by approximately 3 geese. So we had 45 geese, and there was increase in 3 geese in the population, So the total number of geese after 1 year would be 48 geese. And I didn't round down because of logistic growth. I rounded down because I followed normal numbering rules. Okay. So at this point, you should have done 1 and 3 on your own. I did 2 with you. I did 4 with you. And now you need to do 5, 6 here, 7, 8, and 9, and then stop here. Okay. So please take a second to work on those.